Hi everyone. Today we are going extremely lucky to have with us Imdad Ullah on our Meet the Young Professional series. So he's going to be talking about the semiconductor industry, Moore's law, and future of computing. So Imdad Ullah is currently working in the LSI Solution Division at TOSHIBA Systems, Japan, and he is also pursuing a PhD in Information and Computer Science in KEIO University. He's currently actively involved in ASIC or System on Chip design, and he also worked while he was in BUET during his undergrad on System on Chip design. So without further ado, I would like to invite Imdad to share his talk with us. Thank you very much.
Thank you everyone for joining this today's session. Good evening. My name is Imdad, as Sajid sir mentioned about my intro. So thank you for giving me this opportunity to talk about the latest trend in semiconductor industry and also the current know-hows in this industry who are interested in this domain. So let's get started to today's presentation. So basically, I choose the topic as per my observation of the current trend in this semiconductor industry, because as the computing is changing very rapidly with time, so we have to think about what is currently happening and what is in the future. So based on the fact, I am going to talk today about overall the semiconductor industry in a nutshell. So basically, Sajid also introduced initially about myself. I graduated from BUET on 2013, and after graduation, I joined Prime Silicon Technology, which is a USA-based chip design company. At that time, it was a branch in Bangladesh also, and now it is also operating. And I worked there 2.5 years to do some SoC design, which is actually on that time, it was I was lucky enough to involve myself 2 or 3 good tape out projects, which are really enhanced my experience in the VLSI domain. And after that, in 2015, I moved to Japan, and also I continue my job with the SoC design and development. And in 2018, with this job, I also started my PhD in KEIO University. My PhD is on the same domain in the semiconductor industry, VLSI, but the topic or the theme of the PhD is a bit different from the ASIC or SoC. It is actually reconfigurable computing. So in today's talk, I will try to cover the both type from my experience in job and from my experience in academia. And currently I'm working as associate specialist in TOSHIBA in the LSI Solution Division. So my research interest is actually on ASIC or SoC design and development and verification with low power intent, and also the reconfigurable computing sector with high performance computing. And I'm particularly interested about bioinformatics or computational biology related applications, and also multi-access edge computing, which is currently is in good buzz in this industry. So in today's talk, I will actually divide my talk into 2 parts. In one part, I will try to explain ASIC and SoC, and the later part, I will try to explain on the reconfigurable computing. So today's talk will be outlined as below. So initially, I would like to talk about a brief introduction of the Moore's law, actually, which drives our semiconductor industry for a long time. And then I will briefly discuss about the current semiconductor industry trends. And from that perspective, I will explain few parts about SoC and ASIC development and design flow. And then we will move to the high performance reconfigurable computing part. And as today, there are lots of people are from different backgrounds. So I will try to cover the basics about this industry. And also in some part, I will try to go further detail and discuss about some core topics as well. So, and one thing, just to make it clear at the very beginning, that my talk, or today I'm going to discuss everything on the design and development perspective. So if you are very familiar with the device research, uh, or another part of the semiconductor industry is the actual fabrication of the chip. So this will not be covered in this topic. So I will be mostly involved in the actual project that we do on the semiconductor industry, in the design phase, and also the planning phase, and also the future of computing, how the market will be going on in the future. So that will be the overall scope of this talk today. So let's move on to the today's first topic, which is Moore's law. So actually, what is Moore's law? If you are on the electrical engineering background, you must hear about this term continuously from the first year to up to the graduation. So actually, if we say the exact terminology or exact definition of the Moore's law, it will say that the number of transistors in a integrated circuit will be doubled in every 2 years. So that was the basics definition of Moore's law. Actually, that was not a defined law. It was a kind of statement. And because Gordon Moore's was very popular on that time in 1965, where originally he was tell it as a statement only, and seeing the trends of the emerging field in the semiconductor. So after that, actually, the whole semiconductor industry drives basically with that statement and become it the Moore law. So actually, we must say that we actually achieve this law further than the expectation. As he was mentioned, actually every 2 years, but physically we saw that we achieve actually in 18 months. So basically, it was a great trigger or a great motivation for the industry professionals to further reduce the chip size and also do the high performance with the reduced cost and area. So actually, he was given that statement in 1965, but this statement actually create a predictive roadmap that spans nearly 5 decades. If we say precisely from 1971 up to now, exactly 2020. So these 50 years, actually, the whole semiconductor industry is driven by this law and its subsequent progresses. So if we see the total evolution of the chip size, these actually, as very often we actually hear the term that the 5 nanometer process or 16 nanometer process. Actually, what is this nanometer? Actually, this is the channel length of a MOSFET, where the from where actually the every chip or every ASIC is actually built on. So this is the basics, fundamental part of any chip, and is the MOSFET and the transistor level design, that basic, the minimum channel length that can be achieved up to today is 3 nanometers. So actually it was started from 10 micrometer around that time when Moore actually gave that statement in 1971. And if you see the growth of that shrinking of the channel length, up to 2001, there was up to 130 nanometer channel length was achieved. And after that, in last 20 years, actually we reached up to 5 nanometer, and in future, within 2020, 3 nanometer tape out is projected. So actually what implies here that these transition from 10 micrometer to 3 nanometer, what actually we achieve? Actually, we achieve high performance with reduced area. And one major thing that we didn't focus that time was the power. So actually, this actually triggers that many professionals or many people will say that Moore's law will be going to dead up after 2020 or 2022, because the fact that it is not possible for the industry to actually go through only with the minimization of the channel length or only focus on that area. So actually this gives us the clear borderline that where we'll be focusing on the next future. So we will be talking about this in the subsequent topics. So here we can summarize that Moore's law obviously uh, gives us that foundation of the where the VLSI industry or semiconductor industry is going to be progressing. So based on these, these three factors are the most challenging factors. There's always trade-off between, if you want to design any chip, these three factors will be coming anyhow. So we have to balance these three parts: performance, power, and area. Sometimes it's called PPA. So we have to always trade off between these 3 points and do our design. So let's talk about the semiconductor industry trends from now on. So as I mentioned before, that from 100 micrometer or from the below nanometer technology, our cost was very reduced. But on the latest technology, our development cost is very high. As you can see from the figure, that on the 65 nanometer development cost was less than 50 million USD, and the return on investment was pretty good compared to that time. But on the gradual increase in the process node, if we see from the 65 nanometer to 28 nanometer, 22 nanometer, and on the 7 nanometer, you can see that the development cost actually is very high, around 400 million USD. And this is true that this is very tough for the big companies also to do a chip with that amount of investment if they don't very sure about that in the future market. So from that perspective, we are saying that Moore's law, or the only perspective we have been seeing from the last 50 years, is going to change in the recent future. So this is the main motivation of this project trajectory, that in this 7 nanometer, our return of investment must be 4 billion USD, which is somehow is very critical target to achieve. So that time we have to actually think about what will be the future, and also we have to think compromise our performance, power, and area, those three critical points. And here in the different colors, we have seen the different phase of this whole chip design process. So in the later part in my talk, I will also explain the different phase of a development of a chip design. So if we say only the basics, I mean the main phase, we can say first we have to fix the IP, and then we have to fix the architecture. Then we have to verify that our design is good enough for actually physical design. So then we move out to the physical design, and then few software and firmware development is needed, and then the validation that this chip is going to work in the actual chipset or actual device. And this whole compromises actually the cost of whole chip development process. So this is the overview of the how far we can go in terms of the cost and investment, or cost and profit trade-offs. So next, we will see that actually after the Moore's law, what is going to happen in the near future, or actually it is happening now as well. So as I told you before, that Moore's law actually dominate this industry for 50 years without any, I mean, doubt. Undoubtedly, this is the most predominant motivation for the semiconductor industry. So actually that time, what was the motivation and what was the actual objective of the computing was general purpose computing. That means you are creating something that will actually do some general purpose rather than very specific task. So if you remember like the last 10 years, you will see that, okay, next year there will be a faster processor is going to come in the market. Then after 2 years of, or less than 2 years, we see a new version of the new processors. So actually those computing was actually general purpose computing, like the CPU we have in our PC. So in 2005, let's say we have Pentium 4 in our PC, and then later on, like in 2010 2010 or 2007, we have Core i5, Core i3, Core i7, different kind of processor, and different kind of generation is evolving. Actually, those are triggered by the Moore's law. Actually, those processors are the general purpose processors, which is good enough to do some general purpose computing. But from that viewpoint, we are now focusing actually, currently this is also happening, is the domain specific computing. That means your hardware will be targeted on a particular domain. It will not just do the general task only, it will be specified for a particular task. So this term is very common in this semiconductor industry for the last 10 or 15 years, which is called domain specific computing. So actually, why we focus on the domain specific computing? So it is more increasingly challenging to achieve performance with the generalized hardware. So we move on to the domain specific computing. So basically it improves the performance with a specific domain, and then we can achieve that purpose with a limited amount of cost. So what is actually domain specific computing? Actually, this consists of the general purpose computing and also plus something. So that plus something is actually the hardware accelerator, memory, and IO devices. So we cannot say that we don't need CPU anymore. We will do only other stuff. That is not possible. So we have to do something that is combining of both the CPU and also the other devices. So that actually triggers the domain specific computing. And in this domain specific computing, actually the domain or the task is accelerated by ASICs, FPGAs, and GPUs, and also SoC. So these are the different platform you are going to have in the future or in current phase also. These different kind of accelerated device, and the thing that which device or which part is good for your project or for your product is basically is largely depend on actually the cost you are trying to project, and also the performance you want to get, and also the time to market. So considering those factors, we are going to achieve our specific task with our specific domain specific computing. So let's move a few of the basic industry trends now and also in the coming future. So you all know about you also know about the ASICs, or at least you hear the term that ASICs, SoC, FPGA, those big terms. But actually, what are these terms? So if we start with the ASICs, ASICs actually stands for Application Specific Integrated Circuit. So actually, all of these are designed for a specific task. So ASIC is also designed for a specific application, and it can incorporate both the analog and the digital. And it is also possible to have only digital circuit as well. So sometimes we call mixed signal IC, which is actually what is meant is actually the both the analog and the digital portion is exist on the chip as well. So what is the actually pros and cons of the ASICs? So if we say the good point is it is very efficient. I mean, from these three parts, ASIC provides the highest efficiency, but the problem is it is very costly. The thing is that if we want to do some bulk production, like for our smartphone, like every year Apple release new uh, uh, SoC for their new iPhone. So if we say for the iPhone, it is kind of like bulk production in the manufacturing. So in that case, ASIC is the best option for the bulk production. So although the non-recurring engineering cost is very high, but it is very cost effective if you go with large volume. So if you specifically target for a targeted hardware, then ASIC is a very good choice. Then it is also possible to do with the SoC. So actually, sometimes we use the ASIC and SoC interchangeably. So actually, what is different in SoC is that here, system on chip. So that means not only the computing system, other peripheral devices is also accumulated in the actual chipset. So here the memory and the IO devices is also there. So actually in terms of the efficiency, both are same, ASICs and the SoC. So here also the points are similar, like the initial cost is very high, development cost is very high. So if you are sure that you are going to do with uh, bulk production, then SoC and ASICs is your good choice. Then comes the FPGA. So actually what FPGA means is field programmable gate arrays. So you may hear the name that in the current years FPGAs are having buzzword in the semiconductor industry. So actually what differs FPGA from ASICs and SoC is the configurable architecture. So what does it mean? It means that ASICs and SoC are frozen. That means once you finally design the chip and you go for the fabrication and you make the chip, that means it is frozen. You cannot change anything in the design itself or in the chip itself. So these are frozen. So that means if you do any mistake or if there is any bug in your design, you have to do the whole process again. So this is the major triggering point for the FPGA design. So FPGA is also good for prototyping. If we want to do some ASIC design or SoC design, sometimes we do some prototyping on FPGA to check that whether our design is perfect or not. Then we go for the actual fabrication of the chip. So from that perspective, FPGA is also used very popularly nowadays. And initially, actually, FPGA was thought about like prototyping, or it will be do good for the lower speed or low level of applications. But nowadays, FPGAs are very compelling because nowadays FPGAs are very powerful, and actually lots of varieties of design can be done in the FPGA. So in a nutshell, we can say that ASIC, SoC, FPGA, it's all about your design, all about your project, what is your target and what is your requirement. Based on that, you actually choose what the process or what the uh, method or the device you are going to take. So we cannot say that this will be obsolete in the near future. We cannot say this will be the dominant. Actually, all thing will be there, but it will vary depending on the applications and depending on the market requirement. So here we will show some comparison between different types of uh, architecture. So here I have shown the two currently dominant industry or market segment, which is deep learning. You may hear it every day, maybe nowadays. So deep learning is one, and another is the genomics. So due to the COVID, everyone is curious about health related research, but actually before that, actually in the last decade, from the last decade, actually lots of bioinformatics related or computational biology related things are happening, and it is going very steadily, I should say. So I choose two dominant domain in here to actually visualize the comparison between the different architecture. So if we first go to the deep learning phase, so here you can see that the CPU is actually very low in terms of the performance if we say specific computing. That's why in my previous slides, I mentioned that from the general purpose computing, why we actually shift into the domain specific computing. So we can say that in the both example, actually CPU is performing lesser than the other three. So for the deep learning application, we have shown the metrics, the per watt images it can be processed in different architecture. And for the genomics, actually how molecular cells can be computed per watt. So in terms of power efficiency, we can see that CPU ASICs actually is very good for performance. So actually, as I told before, that ASIC is very good with highest efficiency, but the only problem is that if you do not go for the bulk production, it is highly expensive. So as you can see, that deep learning and genomics is actually a very targeted design. So you cannot go for the bulk production unless and until it is actually required. So in that perspective, we can say that CPU and ASICs are the, although in this diagram, but is not, I should say, the optimum choice for our case. So what we can see in the deep learning, GPU is actually doing good in deep learning tasks. Say for example, this is actually showing data for the ResNet application with deep learning with many hidden layers. So we can say that different kinds of computation can be done with very good accuracy and good performance with the GPU. And in the genomics, actually GPU is less good choice in terms of the power efficiency, because in the genomics, the computation, we don't need very specific digital signal block. So that's why the normal FPGA logic can be is enough to do the processing. So in that case, FPGA is good choice if we think about the power efficiency. So this is the kind of overview of the today's choice in deep learning or in genomics. So let's do at what we should focus on the future. So here we can see the different domains that is actually trigger our different domain sectors in the semiconductor industry. That one big topic is advanced driver assistance system, which is called ADAS, which is actually different from the autonomous vehicle, where autonomous vehicle is different division is there, but the ADAS is kindly slightly different, which means that driver will be there and driver will be assisted with some kind of extra device or extra knowledge. So that is actually part of the ADAS. And we also know about the IoT and augmented reality and the virtual reality. And also 5Gs are coming. That means that we need high-speed processors to actually in our smartphone and smart devices. And also big topic is the multi-access edge computing. It is a very good topic and hot topic, I should say, because when 5G is coming, then the whole processing, it will be done on the edge. That means on your side. Right now, if you want to see a movie in the YouTube or any video in the YouTube, that means your request is going through the main core server, and then you are getting all the data through that server. But in the multi-access edge computing, the whole computation will be done on the edge side. That means your data will not be sent to the main cloud, it will be sent to the edge, and then it will process and give you the feedback. So that means it is a very good choice for every kind of processing in the near future. And another good choice is the consumer electronics is already getting smarter nowadays. So it needs the good amount of computation and resource for the smart applications, and also the high performance computing and AI accelerator. That means if your artificial intelligence application, it needs a high amount of computation. That means you have to have some hardware to actually do that physical computation. And this is actually, you all know that we are generating huge amount of data every second. So for the data center and for the data storage, there is a great scope for brainstorming in the near future. So here is an example that we developed at Toshiba that perfectly do the ADAS job. So actually this chip is called Visconti, which is the flagship product of Toshiba. So here actually what this chip is doing is actually assisting the driver about the different parameters that is necessary while you are driving, like what is your traffic signal and what is the speed limit of your road, and if there is any pedestrian in the middle of the road, so you will get notified. And also the lane departure and lane detection, that you are going further away of your lane or not. And also the different kind of traffic rules that you have to face in your route. So this kind of processing is done through this chip. So actually this is a image sensing processor with deep neural network. And if you see the architecture of this design, you can see that it's actually complex, very complex in terms of the functionality. But if you see from the design perspective that I told you before, that what are the modules is necessary for a ASIC or SoC, then you can actually relate those from that slide to that point. As you can see that in a SoC, you will have some multi-core CPU subsystem. So that is also present in this chip. And also you will need very good IO connectivity to send and transfer the data within your SoC. So we can see different kind of interface is there, and you actually take the input from the IO interface from the camera. So these are the input IO interface of your device, and these are the different kind of filter or the uh, uh, process engine you are going to have in your actual deep neural network. So these actually comprise the whole system on chip. So, and also you must have some external memory to do your processing. So this is one example of what we are doing in Toshiba, the current image sensing processor. So actually, what is the actual design flow that we are having in this uh, arena? So this is a very generic diagram about the design flow. Those who are very interested about working in the semiconductor industry, I must say that you should focus on the design flow, because it will help you in the later part of your career to understand what the design flow you have to maintain. So it start with the specification that we have to fix, that what is our target, what is going to achieve by our chip. So that is the first step of our design. Then we have to do some design entry. That means you have to write in HDL, any hardware description language, your code, that what is the actual functionality of your device. Then you have to do the functional verification. Then you have to go the RTL synthesis. That means you define your device, or you define your functionality in a very high level of abstraction. So you have to get level abstraction. So that part is actually done by the RTL synthesis. Then from the 4 to 9 is actually the physical design, we say physical design of the chip. So here actually you like doing a building. When you are creating a building first time, you have to partition the floor plan, that where the rooms will be allocated. So like similarly here in our chip, we have to design the partitioning of different kind of blocks, that where will it be placed. So this is the initial partitioning of the chip. Then we have to do some circuitry for the design for test. So this is actually required for later on in the process. When we fabricated the chip, we have to test the design. So for the test purpose, we have to insert DFT circuit in our design. Then we do the floor planning and placement the design. And the eighth step, which is very important, is the clock tree synthesis. That means you have to propagate your source clock to every flop of your circuit. So that part is very crucial in a very latest technological node. And then if your clock tree is done, then we will go to the routing stage. And after the routing, we will do the final verification. So actually here with final verification, we mean that both the static timing analysis or timing verification, and also the physical verification. So if both of your verification is passed, then you generate the GDS and go for the tape out or final fabrication of the chip. So these steps actually takes a lot of time in the development phase, because these are kind of trial and error, or not, I shouldn't say trial and error, but if you have any kind of timing violation or physical violation, you have to go through step 9 and 10 quite a lot of time, because once you fix the timing, you may have some additional physical violation. So you have to fix those physical violation and then trigger some kind of timing violation. So we have to look through this kind of process for quite a lot of time in the current process node to achieve the accurate design. So you can imagine from this step that whole this step, there are a lot of team is involved. And uh, if we say step 1, 2, 3 is kind of one design part, and 4, 5, 6, 7, 8 is another team of the design, and if, the 10 is dedicatedly a team is assigned for this kind of verification. So actually a lot of people are involved and a lot of resources are required. So that's why actually the semiconductor workflow is actually takes a lot of investment actually to do the actual design. So now I will say about something about the reconfigurable computing. So far we have discussed about ASIC and SoC development. So this is part of my research where I'm engaged in my PhD research, where I'm working on the reconfigurable computing. So actually what is high performance reconfigurable computing? So actually it is a regular computer architecture, but the main thing is that we introduce some flexibility of the software from the very higher level of abstraction and implement in the hardware. So we can say that it creating a bridge between software engineers and the hardware engineers. So sometimes software engineers are not familiar with the hardware. So they cannot write HDL, I mean hardware description language from a software perspective. So that actually helps for the software engineer to define their hardware abstraction from the higher level of abstraction and then implement those in the actual hardware. So this is actually comprised with regular processors and also with FPGAs. So FPGA is good for in this perspective because of high performance and low power. And nowadays in computational biology and financial computing and also in the high throughput data search, this HPRC is used extensively. So here I am showing few example of the high performance reconfigurable computing. It is called Project Brainwave. It's actually flagship project of Microsoft for their Bing search. Actually, you can see a drastical improvement in the Bing search in recent years. Actually, they leverage the processing of the Bing search through reconfigurable computing. The architecture is something like that, that you have the CPUs like you have, and the main thing is that you are connected with FPGA, and this FPGA is connected with the NIC and TOR, which is transferring or communicating with 40 gigabit per second speed. And with that, you can achieve a lot faster acceleration on the FPGA fabric domain. So in this domain, the every dot is actually here for kind of FPGA fabric. So you can see that lots of FPGAs are there to actually connected those fabric, and this is the actual hardware acceleration plane, and these all are connected with the CPU. And actually what is happening in this hardware acceleration plane is that in a search engine, you have SQL query and you have the search ranking. Those workload is actually done in this fabric. So these all FPGAs are connected with high speed link, and they can communicate with faster throughput than the traditional computing. So this is one project of Microsoft Project Brainwave. Then another project that I am currently working is it's called Flow in Cloud. We call it fixed system. Actually, this fixed system is a multi-FPGA system where a lot of FPGA is connected with a circuit switching network, or we can say that STDM, static time division multiplexing. The main motivation of this is that although there are a lot of FPGAs are connected with the high speed link, but from the design perspective, we will see that all connected FPGAs are working like a single FPGA. So that means you can have higher workload and higher processing on a cloud level. So that means on the cloud, you can implement your design, and from that part, you can process your design with a very high speed and high performance. So this orange portion of this FPGA is the actual user application module that you want to design in your FPGA. So this is the current structure of the flow in cloud system, and it is a good structure if you think about the multi-access edge computing. Like I said before, that in multi-access edge computing, actually you have to compute the whole processing at the edge site. So that means if there is any IoT device or any kind of industrial IoT device or any kind of business transformation system device are there, any sensors or any automotive that are driving through autonomous vehicle, those whole data will be sent to the multi-access edge server, and that server will process the workload, and then it will divide the workload and process the design, process the application, and then subsequently send the result to the respective workload. So that means you need a very high efficiency and with low power, obviously, because you will not try to spend more amount of money on the powers. So you need something that will be high performance, low power, and high throughput. So that is why we are seeing that this multi-FPGA system is very good in terms of the future computing. So another good application is the genomic sequences analysis, which I am actually currently working on with this system. The main motivation, or I should say the objective of this computation, is the precision medicine. So currently we are all having the COVID situation. So that means you may also heard that new sequences of COVID-19 virus is actually exploding every day. So different kind of genome is there. So what we have to do in bioinformatics is we have to analyze those sequence, but those sequence can be very large. For example, a human genome, a full genome, is comprised of actually 2 billion base pairs. So that means you have to process heavy amount, lot of amount of data within a very shorter amount of time to actually do the whole process. So that's why actually we need some kind of acceleration in the genome sequences analysis part. So for the COVID-19 virus, this virus is not very larger, so it is very smaller in size. So any kind of CPU based acceleration is suitable for that part, but we are thinking about the actual precision medicine. That means in the future, say for example, we have fever, we got medicine from the doctor, but this medicine can be same for the all of the patients. But in future, there will be some precision or personalized medicine where you will be given a particular medicine only for you, not for the other patients. So for that purpose, you need actually the whole genome sequencing analysis. So actually, currently the next generation sequences devices, it can generate millions of short read DNA fragments, which we call short reads. So here in this figure, we can show that there is a reference genome, like your father or your mother, you have the reference genome, and from the next generation of sequencing, the sequencing device will create millions of short read, like this kind of short amount of read for your genome. And the purpose of analysis is that you have to map this genome to the reference genome and construct this output sequence. So from that perspective, you can see what are the difference from your reference sequence and your output sequence. So if we say the reference genome, reference sequence is from your father and output sequence is of yours, so there is a genetic variation that in this case, we see kind of genetic variation from you and your father. So that means you have some genetic feature, which is good information for the doctors to diagnosis your different kind of treatment or different kind of disease. And actually this will be very helpful for the cancer research and also the genetic diseases we have. So this is one example that we can think about in future for the reconfigurable computing. So in this domain, like high performance reconfigurable computing, what are the design flow? So like the ASIC and SoC design flow. This design flow is almost similar. You can see the whole design flow. It might be look quite complex at the very beginning, but if you see the basic steps, so the first step is you have to design the system level design, then you have to do the physical design. So in the system design level, what is the most crucial part here is that you can specify your design with C or C++ level abstraction. That means you don't need to do the actual HDL, I mean the hardware description language. So if you are a hardware engineer from the beginning, you can do the HDL by yourself. And if you are a software guy who is not familiar with the HDL, you can start with your design with C or C++, and then you can do high level synthesis. So this is actually do the part which is actually translate your design in the C and transform it in the hardware description language. And once you have these, the RTL of your design, then the subsequent step is almost similar with the ASIC or SoC. So here is the big advantage of high performance reconfigurable computing is the software designer can also work on this domain. So if you can design your circuit from the very high level of abstraction and then do the subsequent stage at a easier pace. So this is the basic generic flow of the high performance reconfigurable computing. And then I will briefly discuss about what is actually high level synthesis. Actually, high level synthesis bridges hardware and the software engineers. So it is actually a design process that translates the higher level of abstraction to the hardware level of abstraction. So that means you can develop your algorithm in C or C++, and then you can do the high level synthesis and your RTL will be generated by the synthesis tool. So after that synthesis, you can implement your design in the actual FPGA. So here, what are the difference between the software part and the hardware part? Here I have shown a basic comparison between the software part and the hardware part. Like in software, we define the top level function. So when you design, when you specify your top level function in your algorithm, that will actually translate your top level function to RTL's IO port. So that means in your RTL, you need IO ports. So that IO ports will be automatically imported from your top level function definition. And in your algorithm, you will obviously define few or many kind of functions. So those functions will be actually different modules of your RTL code. And in your design, you will define different kind of arrays. Those arrays will be actually translated into the block RAM of the FPGA. So here you can see that although you are defining your design on the C++ level, but HLS helps you to achieve this in the RTL level. So nowadays the tools are very good at implementing different kinds of high level synthesis. And if you're a hardware guy and if you are confident with your hardware level language, so actually you can go directly to the HDL and do the RTL synthesis and the subsequent stage. But it will be benefited for those who are in the software phase who are not familiar with the HDL. So in the next part, I will briefly mention few other research which is currently in the semiconductor industry. One is neuromorphic computing actually. I will talk slightly about this neuromorphic computing in the next slide. And other research trends is quantum computing hardware security. Hardware security is very important in terms of the IoT, because IoT, there will be a lot of IoT devices in the near future, but the security is very important, because if the security is not achieved, there are a lot of casualty or a lot of dangerous things can happen. So hardware security is another very good research trend in the semiconductor industry. And also the low power transistor, as I said in the very beginning, that Moore's law actually is going to dead because of the fact that the transistor is consuming large amount of power. So we have to have some low power transistor. And also another big thing is the memory and the storage device is a very good research trends in the coming future. So just I'm explaining something about the neuromorphic computing. So actually neuromorphic computing is a regular thing, just the term is name is different. What it is actually, it is normally the usual VLSI system, but the main is that it will mimic the neurobiological architecture that are present in the biological system. So what it means is that in the first generation of artificial intelligence, actually the AI was working on the very specific domain. Like if you define some rule, and your AI model will give you that result. Okay, this is okay or this is not okay. But in the current generation of AI is actually depending on the sensing and perception. That means you have to have some knowledge about to sense and about to decision making based on your perception. So for that perspective, actually neuromorphic computing is very good in the future, and it is an interdisciplinary field because you need the biological system, what is the physics, math, and also the computer and electrical engineering. So the main motivation here is to you do some computation. Keep in mind that it is actually the mimic of the biological nervous system. So this is another interesting topic for the next future. So that is overall topic of my today's talk. And finally, this slide is for the newbies or the students who are very familiar or very interested to work in the semiconductor industry. I will just briefly explain some of the recommended skill set that are necessary to work on this domain if you're really interested. So from my experience, I can figure out those skill set. So first is your fundamental of VLSI knowledge. This is very important that once you are in the semiconductor industry, that means you have to have some core knowledge of VLSI. Then another big important point is the design flow. In the ASIC and SoC and also the reconfigurable computing, I have talked about the design flow. So you have to have very clear understanding of the design flow of the architecture. And in the actual design, we use a lot of EDA tools, which is called electronic design automation tools. These tools are very efficient in terms of the performance. So you have to know the tools mechanism. This is actually not possible unless you have the actual project. But once you get the project, you have to have uh, curiosity to know the tools mechanism and also the tools commands and reference. And another skill is very important is your scripting skill and debugging skill. Here, not the regular programming skill, but scripting is very important. Like with Perl, Python, or Shell, you can text process different kind of results and report. This is very important skill for you to do the task. And finally, the whole work environment is on the Linux. So you have to have very proficiency in the Linux command line environment. So if you have those kind of skill, I think you are very ready for the market. So this is the overall recommended skills that I can prefer for you in the coming future. So this is the all for today's talk. So I try to uh, cover my work and research experience, and hopefully you'll get good idea or any idea from this semiconductor industry, and that will be helpful for you in the future. So thank you very much for your patience and time for today's talk. That's all from my side. So if you have any questions or any comments, please feel free to ask or feel free to share. We will have kind of casual discussion afterwards. Thank you very much for your time.
Thank you very much, Imdad, for the really nice and informative talk. And I think this talk was primarily focused towards the graduate students, but
Okay.
I also invited a lot of the undergraduate students to come here to learn about the industry trends.
Mm-hmm.
Particularly, I also shared it to the students of my class to
Okay.
come and listen to the talk. So
Okay.
the floor is
Thank you.
now open for discussion. You don't have to necessarily ask about the semiconductor industry. Ask any questions regarding career advice or in general electronics. So please use the raise hand option, and then I can see who wants to ask the questions. So everyone
Hi, I'm MD Sajid Hussain. Can I talk? Although I'm not a student right now.
Sure, sure. Go ahead.
Yeah, thank you, Imdad Bhai. I know you from Japan. I had to work in the Hiroshima University, as I talked with you before.
Mhm.
Hello.
Yeah.
Okay. Yes, I can
Yeah,
hear.
thank you. So, especially my field is actually I work on RF circuit, analog RF circuit design. So, particularly, it's a very different side from your research part. So, I have some questions regarding your talk. That
Okay.
you told about the Moore's law and the trend of the Moore's law. So actually, when this transistor will shrink in the next 2 or 3 years, what will be the DIBL effect? I think that it means drain induced barrier lowering, as you know. Now, what kind of DIBL will affect on our designing transistor? And another question is, you presented your Toshiba chip, Visconti processor. Here you told about the deep neural network. So actually, how much time is needed for the image detection and the retrieving this image by using your chip and then response? So how much time needed to respond to this all kind of operation using this Visconti chip?
Okay. Okay. Thank you very much for your question. So in terms of the first question is that the Moore's law and the transistor level research or device changes. So actually, at the very beginning, I mentioned that the research that we are having on the device level is completely a bit different from what is actually going to develop in the actual circuit. So in terms of the transistor level, there are a lot of changes happening nowadays. As I mentioned, that low power transistor design, that you have mentioned a lot of issues that we are having. So this kind of research topic is also critical in this current phase, because only the fact that we cannot shrink the channel length, because the other subsequent effect that we actually didn't notice, or I should not say didn't notice, actually we didn't emphasize on that earlier stage, because on the earlier stages we only focus on the performance, I mean the high speed. But at this current level, we are more focusing on the low power as well. So this is a kind of trade-off based on what your device is going to do in the future. So if you more focus on the power side, you may have to come up with the low-level transistor design by successfully defending all the challenges there. And in the if you want to have the high-speed design, then you have go for the latest technologies, but you have to keep in mind that you may have ended with the high power. And the next question is about the Visconti processor. So this processor, actually the main motivation or main motive of these processors is actually to give you the exact timing. So we cannot say that how much time that like 5 seconds or 2 seconds to do the computation. It all depends on the current exact situation on the road. So basically it triggers, or it detects all the features spontaneously at the very instant of your driving. So that means that you have that's why actually these devices are called assistive advanced driving assistive system. So that's the main purpose of these devices. So we cannot simply say that say for example you are going on a highway with a very high speed, and there are not too much to think about on a traffic. So that time the competition is quite different than the regular traffic. When you are in a busy road, the competition needs to be very currently, I mean, faster processing is needed with lots of road sign, pedestrian. So that time it's much faster from the human to actually detect. So we can say in terms of the timing, we can say that this is actually assisting the drivers to take the decision more quickly than the manual intervention.
Okay. Thank you. I understood.
Okay, thank you very much.
Thank you for presentation.
Thank you for the nice question. And
Yes.
I mean, as Imdad mentioned, he works on the high level designing part. So right after Eid, we are hoping to have Mr. Dr. Raisul Islam to give another talk. So he exclusively worked in global foundries on the actual fabrication part. So he could also give his perspective on regarding how small we can shrink the transistor. So please stay tuned in our Facebook page for his talk. So next question is from Ramit Dotto. If you could unmute your mic and then ask the question.
Thank you, sir, for giving me the opportunity. My question is, what are the resources, online resources for like paper or books to get insight and in-depth knowledge of neuromorphic computing? Because there is some shortage in this particular topic of resources.
Okay. So this is a very good question. So as this is very good, I mean, very in a new, I mean, the very earlier stage of the neuromorphic computing. So what I suggest that you must have some basic understanding of the VLSI system itself. Actually the design motivation is actually changing, but the main core concept is same in the neuromorphic computing as well. So first try to basic understanding of the actual VLSI system design from the ASIC to FPGA or any kind of architecture. You have to first the basic foundation of the architecture of a VLSI system, and then on top of that you can see what application you are going to implement on those architectures. Then comes the neuromorphic computing. So actually neuromorphic computing is, we can say that the application plus the architecture. So you have to do the both. So first do the basic architecture study, which is very available in nowadays because the industry is going through it for a long period of time. You can go through different kind of computer architecture book. And for the particular neuromorphic applications or neuromorphic computing, you can focus on the researcher who was particularly working on that. I can mention one of my friend who is called Ahmedullah Aziz Rafi, who is at the Tennessee University assistant professor. Recently he joined there. He's actually working on the neuromorphic computing. So I can share the link of his page. His lab is called Nordic Lab. He's working on the neuromorphic computing as well. So if you're interested, you can see his research page also. He's doing very good in this domain.
Thanks for that.
So I also plan to bring Ahmedullah Aziz Rafi. So he was in the same grad school as where I went to Purdue University. So hopefully we would host him in a future event here as well.
Yes.
So next question is from Ifat Mahmood. If you could unmute yourself and then ask the question.
Thank you, sir. I'm Ifat Mahmood. I am a fresh graduate and I want to build my career in VLSI design sector, but I actually don't know where to start. Which software should I learn, or how can I get the resources in these sectors like the VHDL or Verilog? In some cases, some say VHDL is used. In some cases, they said Verilog is used. So, what should I learn as a beginner?
Okay, got it. So maybe it is a common question for all the new grads or those who are in undergraduate level. So first, I must say that first on your undergraduate level or on the current level, try to develop the theoretical knowledge that you can achieve from the different learning materials, like from the books and from the tutorials and from the different kind of internet resources. So once you have got the basics or core knowledge of the design flow, then you can do the hardware description language. So as you mentioned that VHDL or Verilog, both are popular. Actually, you can start anything, but from my perspective, I will suggest Verilog because it is widely used. You cannot stuck anywhere if you don't know VHDL. So there is no chance that you don't need only VHDL. So you can start with Verilog, which is very easy to start with. So try to implement few design in the free student version of the different EDA tools. And there's one good website which is called EDA Playground. Sadiq sir also mentioned in his video tutorial about the EDA playground. So you can go there and write few example codes and simulate their design. And afterwards, you can go for the bigger design if you have the access of industry software. But I'm afraid that in our country or in our level, it is very hard to cope up with the EDA tools because those are too expensive. So you may not get the availability of those tools, but you can get free basic tools which you can use for your learning purpose. And also, if you're interested with the FPGA, so you can download the FPGA design license from the vendor website and implement on your design on the board. So this will another good way to brush up your skill if you want to really interested to work in this domain. So in a nutshell, we can say that first, the theoretical knowledge and the core concept, and second is the practical implementation with the student version of the tools or free tools.
Thank you, sir.
Thank you.
Right. Thank you very much. Yes, for the EDA playground, it was really helpful for me because when we started the lockdown, I wanted something so that even the students could use their smartphones and just play around with the Verilog codes in my class. So then I decided to start using it as a cheap alternative for expensive softwares. So you can go there, and as Imdad mentioned, most of the FPGAs, I think for very less money, you could get a beginner level FPGA to play with, and then it would give you the required licensed software for free. So you could start with playing with those things. So do we have any other questions? Okay. Baria 9, you can go ahead and ask the question. So we don't have any, please unmute yourself and then ask.
Assalamualaikum, sir. I'm Baria Nain. I'm graduated from BUET EEE and currently working as a verification engineer in Intel Semiconductor. I'm currently working in RISC-V processor verification. So my question was that I found Bangladesh is very backward. I mean, when I was searching for job, I saw very few VLSI industry in our country. So for long-term planning, if I want to cope up with this field, or if I want to stay in this field for long term, which countries or places are safe, or what is the recruitment process of these abroad industries?
Okay, yes, you are right that in Bangladesh, actually, we don't have the very good work environment for the semiconductor industry yet, because actually the main problem, I should not say problem, the main challenges are the big investment actually needed. So that's why actually this industry is not growing that faster compared to the other industry. And also in that industry, we have to have some very strict deadline. So you cannot just train engineers and do work because you cannot achieve the deadline. So that's why a few challenging factors are there. So if you are interested about VLSI in your future career path, so I must say Japan is also a very good in the semiconductor industry for a very long time. USA is also very good. And there are lots of companies, although I mean they are maybe Japan-based company or any other country-based company, but they have offices in different locations in the region actually. So if you say the region-wise, so there is a one Asia-Pacific region, and one is North America region, and another one is Europe region. So you can go with any either of this region based on your preference. And one good advantage in VLSI is that unless I mean you don't you just do the hobby work, if you do any kind of industry work, that will obviously help in your next career path. So you may work in Bangladesh for a one project or in two projects, but this must help you in your next career path, because as I told before that EDA tools are very expensive, so you cannot download those tools and learn by yourself just for hobby. So these requires that you have this kind of dedication and interest. So that means you have worked or on very good projects. So that is actually very helpful for your future career, wherever it is. It may be in Japan or China or in the Asia Pacific region or in the US or in the Europe. So I advise you to achieve as much as you can in your current job, because Neural is also doing good. Try to learn more thing on a real project base. So the more you learn and the more it will help you in your future career. And I mentioned in the recommended skill set, so try to get those skill set as efficiently as possible. So that will obviously help you in the future. Thank you.
Thank you very much. So we probably have time for one last question. Is there anyone who want to ask a question? Then we would take a group photo with all the participants.
Sir, I want to ask a question.
Go ahead.
Sir, so I'm Asif Hussain. Sorry for disconnected for a few minutes. My question is, what is the trend actually of semiconductor industry? Scaling or clever design with scaled device, the existing scaled device?
Okay, so actually it depends on your target. So if you want to, like say for example, if you're the designer of the iPhone or any kind of new device, so if you say that your main phone size must be limited with a certain area, so you have nothing to do with the other thing than the area. So that means you have to focus on the scaling. But if you're focused on the very specific or very domain specific computation, that time you may not focus on the scaling, but you should more focus on the computation power, because if how much power is consumed by your device. So that is very crucial point on your design perspective. So the main 3 points, the performance, power, and area. So based on these 3 factors, you have to keep a balance based on your target architecture.
Okay, based on my application. Thank you, sir.
Yes, yes.
Thank you very much, Asif. I would like to invite everyone at this point, if you're comfortable, to unmute, turn on your webcams so that we could take a group photo with all the participants. And with this, I would like to thank all the participants who have come here, and I would like to thank Imdad, who has taken this his time to make this wonderful presentation of on this topic.
Okay, thank you very much, everyone.